Now that we know the definition of what a function is, we're going to start to look at all the different types of families of functions that we're going to want to eventually do calculus with. And normally when there's people in the room, I will ask them what is the type of family of functions you'd like to look at first, and I can rely on the fact that they will always say linear functions. It's never been any otherwise. Nobody has ever said we'd like to start with the inverse trigonometric functions. So we're going to start with the linear functions here. All linear functions take a certain basic form. So if y equals f of x is linear, we can write y equals f of x equals mx plus b. So every linear function can be put in this particular form. And I think you know that the m and b are what are important here. So m is the slope of the function. And then the b is the y-intercept. And remember, the thing you have to remember about the y-intercept is that the y-intercept is actually when x is 0. So if I were to plug in 0 for x, we get m times 0. That term would go away. We'd be left with just b. So the y-intercept is b. And one reason that linear functions are special is that they have a particular quality about their rate of change. The rate of change of a linear function, whether you're going up or going down or going perfectly horizontal, the rate of change is constant. So if f of x is linear, the rate of change, so either the rate of growth or the rate of decrease, the rate of change is constant. Now, almost any time a mathematician sees a statement of the form if then, the mathematician would like to ask, is the converse of this statement true? In other words, if I read the statement backwards, is it also true? So ask yourself now, if you know that the rate of change of a function is constant, must that function be linear? If the rate of change is constant, will the function have to be linear? And the answer in this case is yes, because if you try to picture in your head what it means for a rate of change to be constant, I hope you are picturing a line, and that is what the graph of a linear function looks like. So I'm going to write EX as my abbreviation for when we're going to do an example. We want in this class to look at functions in 4 different ways: as a formula, as a graph, as a table of values, and as a verbal representation, as in a word problem. So this is one thing about reform calculus that was really emphasized, is the 4 different ways to look at a function, and we're going to bounce back and forth between all the different ways this semester. So we don't want to just focus on understanding how to solve an equation, we want to know what the equation means. So in our first example here, it's going to be about an amusement park. So imagine some park with a lot of roller coasters and merry-go-rounds and that sort of thing. So the owners of an amusement park conduct a study and they find out that the number of entrance tickets they will sell, so the tickets to get into the park, well, that's going to be a linear function of something. The number of entrance tickets sold is a linear function. So what do you think it's a linear function of? Well, it could be a linear function of a lot of things. It could be a linear function of the temperature and all sorts of things. But in fact, what they discover is that it's a linear function of the price in dollars per ticket. And I hope you would think that is a reasonable thing to happen here. So the first thing we'd like to do is we would like to find I guess we need some more information about that. Before we can find a formula, we're going to try to find the equation of a line here, right? So we need some information about the line. We either need 2 points or 1 point and a slope. So we'll see what we're going to find here. So they sell 2,400 tickets. If the price is $80. And they sell 2,800 tickets. Now, just based again on what is reasonable, will they sell 2,800 tickets if the price is more than $80 or less than $80? Should be less than $80, right? So they sell 2,800 tickets if the price is $60. Okay, so we've set up the problem. Now our first question is going to be find a formula for the number of tickets that they sell as a function of the price. Price. All right, that says price right there at the very end there. So we're going to have to go on to another chalkboard here. Wrong direction. So there's a problem similar to this on the homework, and the way that people historically get this problem wrong is they mix up the x and the y. So think to yourself right now, which one should be the x and which one should be the y? We're told that we want to find a formula for the number of tickets sold as a function of price. And if you think back to our definition of a function, we said that we say y is a function of x. So in this case, x should be the what? X should be the price, and y be the number of tickets sold. So we know that it's linear. That's how we know that we know that we want something of the form y equals mx plus b. And it's up to us to find the values of m and b. And m is what we should find first. M is the slope. And we find the slope by taking what? We take the change in the y value over the change in the x value. So because we have decided that y is the number of tickets sold, on the top I'm supposed to be taking 2,800 minus 2,400. And then what should I put on the bottom? 80 minus 60 or 60 minus 80? Remember, we have to match them up. So the 2,800 goes with our 60. So 2,800, and then we get 60 minus 80. So I think that's 400 over negative 20. So negative 20. So what does that tell us? So now we know that y equals negative 20x plus b. And it's left to us to find b. And for that, we can just plug in either of the 2 points, whichever one we find easier. So I'm going to plug in the 2,400 and the 80. So for y, I'm going to plug in 2,400. And we've decided that equals negative 20 times x. That's 80 plus b. And I think that works out to be b equaling 4,000. So we've got our equation. negative 20x plus 4,000. But now that we've got this equation, we want to figure out what it tells us. So we want to interpret the various important features of this linear function. So the first thing will be to interpret the y-intercept. So this doesn't mean just say the y-intercept is 4,000. This means what does that tell us in terms of the amusement park? So this 4,000 is 4,000 what? Well, we've decided that y is the number of tickets sold. And as we mentioned earlier, the y-intercept is when x is 0. So it's saying if x is 0, meaning if the price is 0, so if the tickets are free, so if the price is $0 per ticket, so if they're letting everybody in free on this day, 4,000 people will come to the amusement park. So one thing that's important here is to try to get the units right and to spell the word interpret right as well. All right, so that was the y-intercept. The next thing we can do is the x-intercept. Now, with a linear function, it's not as easy to see what the x-intercept is as it is with the y-intercept. When we see this equation, we just look right there at the value of b. That's the y-intercept. We need to do a little bit of work here to find the x-intercept. The x-intercept is when the y value is 0. So we can draw our first graph of the semester. We know that the y-intercept is 4,000, and the slope is negative 20. So we're coming down here like this. The units on the vertical axis are tickets, and the units down here are dollars, and this is 4,000. And the x-intercept is going to be this point down here. So we have to figure out what that is, but as we've just said, that's when y equals 0. So we first need to solve the equation 0 equals negative 20x plus 4,000. We bring the 20x to the left side. I think x ends up being 200. So what does that tell us? That says when x is 200, and again, it's useful to think about the units. 200 what? $200. So if the price is $200 per ticket, what happens? Well, when x is $200, y is 0. So what is this saying? It's saying that if the price is $200 per ticket, nobody will come to the park. That's just too expensive. So 0 people, 0 tickets will be sold. And now that we've got the x and the y-intercept, there's really only one thing left for us to interpret, and that is the slope. And in many ways, the slope is the most important thing of this. We are going to spend a lot of time in calculus finding slopes of nonlinear functions. It's easy to find the slope of a linear function. You just look at the value of m. What's hard, and what's a more interesting problem, is to try to find the slope of a nonlinear function. How fast is some other type of function going up or going down? So we will try to interpret the slope. And how did we get the slope? We got the slope by taking the change in the y value over the change in the x value. So if we were to look at our graph again quickly here, the y values was in tickets, and the x's were in dollars. So when you computed the slope, the units on the slope are what? You took change in y over change in x, so the units on the top part of the fraction were tickets, and on the bottom part of the fraction were dollars. So the units on the slope are tickets per dollar. So what is this saying? We know the slope is negative 20, so every time we go 1 unit to the right, we go down 20 units. So every time we increase the price by $1, what happens? The number of tickets sold decreases by 20. And that's what makes sense, right? We would expect that as you raise the price, the number of tickets sold falls. Or if you want to look at it more optimistically, every time that you lower the price $1, you sell 20 more tickets. So our interpretation here would be that for each $1 increase in price, the park sells 20 fewer tickets. And one last note about this is that in week 4, we'll be doing very similar things. We'll be interpreting slopes of nonlinear functions, and then we're going to have to be very careful not to say one particular thing here, and that's this thing about each. Here we're really justified in saying each, because whether I'm right here on the graph, or right here on the graph, or right here on the graph, the slope is always the same, -20, because it's a linear function, because the linear function has this very special property of having a constant rate of change. So no matter where I am in the graph, when I move 1 unit to the right, I move 20 units down. When we do this for nonlinear functions, we'll have to emphasize the fact that it's just at that particular point that we know the slope. So we won't be able to say anything like for each $1 increase or for every $1 increase, and that's how we will distinguish from that situation to a linear function. All right, I hope you have a good feeling for what a linear function is now and how to interpret it. We have a check your understanding quiz on linear functions for you to do now, so please give that a try, and then we'll come back and move on to the next class of functions.